Okay, so we'll continue our discussion on central forces. Last time we looked at the angular equation, okay, for a spherically symmetric potential, and today we'll be going further and looking at the radial equation. Okay, but before we do that, I wanted to just remind everyone of a few things that we had discussed in the previous lectures. Okay, one of them was that we started with discussion about the angular momentum being conserved for central forces. Okay, so this was in one of the beginning lectures that we talked about, and in this case, what we looked at was that we decomposed and got two equations. Okay, here this is equation 1 and equation 2, and from the equation 2 we derived that angular momentum, which is this quantity mr square omega, which is theta dot, is a constant. Okay, and we didn't explore the first equation much. Okay, and today we'll be doing that. Okay, so in continuation with this, what we also did was we looked at the kinetic energy of a system where we have two masses, and we tried to uh, give an expression for this system in terms of the reduced mass. Okay, so mu here is the reduced mass, and we get r dot, which is the velocity square. Okay, so that was the kinetic energy of the entire system. Okay, and we used the polar coordinates. Okay, and we used the kinetic energy expression, and from this expression we reached a point where we actually used the Lagrangian equation, and from the Lagrangian equation, when we solved for the angular portion, we again got the same idea that angular momentum is conserved. Okay, so essentially when we did the first derivation of angular momentum, we hadn't used the Lagrangian formulation, and in the previous lecture we used the Lagrangian formulation to prove the same thing. Okay, so now we are going to continue and look at the uh, radial equation of the same formulation of a spherically symmetric potential that is present, and you have an expression for the kinetic energy term that is telling you about the entire system. Okay, if you have noticed in my derivations, I have used this letter m in a lot of places instead of mu. Okay, so I just want you to be aware of the fact that when I'm using m here, it is same as using the letter mu. Okay, so this m here is the combined mass, okay, of the system. So it might be confusing at some times when we are doing the derivations, but you should be aware that we have looked at the Lagrangian, and what we are trying to do is we are trying to look at this two body problem, right, where there is some force of interaction between two objects. It can be earth and the sun, or earth and the moon, and in that case what we get is the reduced mass of the system, right? And m here that I use often signifies the reduced mass. Okay, so just be aware of that. So this derivation that we are doing here, okay, I'm using m, but you should be aware that this is the reduced mass, okay, of the system. So let me, okay, because if you notice here in the spherically symmetric potential, if I consider this to be a gravitational potential, okay, which is also spherically symmetric, then there is a small m that comes here because of the two masses. Okay, so I don't want you to get confused that this small m is this m. Okay, so let me just write this as m1 here. Okay, all right, so we want to explore the radial component of this equation now. Okay, we had talked about before that this Lagrangian here is actually dependent on these terms, which is r dot, theta dot, and time. So we had to use two generalized coordinates, r and theta, and now we are going to use the generalized coordinate of r. Okay, so we have our Lagrangian. This is the entire Lagrangian of the system, and we have to explore the partial derivative with respect to r and partial derivative with respect to r dot. Okay, so that's what we need to do. So let's find the first term. So in the first term, we are taking the partial derivative with respect to r, and if you look at this expression here, there is only one term which has this r term, right, which is r square. Okay, rest all terms are r dot and u of r. Okay, in fact, u of r also has a term r, so we have to be a little bit careful. So when I take the partial derivative, I'll get 1/2 m times the derivative of this function, which is going to be 2 r, and then I have theta dot square. So that's my first expression here, and then I will get the partial derivative of this potential. Okay, because u is a function of r. Okay. Okay, so I have 2 and 2 are cancelling, so this can get simplified into mr theta dot square minus du by dr. Okay, so that's my first equation here. All right, so next I want to calculate the partial derivative with respect to r dot. Okay, that's that term right there. So now my r dot term is only in this expression, the first expression here. Okay, so that will be 1/2 m, and then I have to take the derivative of r dot square, which will be 2 times r dot, and since I'm taking with respect to r dot, there is no extra term here. Okay, so 2 and 2 will cancel, so I'm just getting mr dot. Okay, so that is my partial derivative with respect to r dot, but the expression is d by dt of this partial derivative with respect to r dot. Okay, so I have to take the derivative of this term, which is mr dot. Okay, so m is constant, so I will get r double dot. Okay, so now I have my two expressions, 1 and 2. Okay, so I can plug them back into this radial equation here, which is my equation r. Okay, so the equation r will become your mr theta dot square minus du by dr, and then I have a minus, and I have a mr double dot, which is equal to 0. Okay, so all I've done is I've taken 1 and 2 and plugged it back into this equation r. Okay, and from here I can simplify it a little bit further, and I can say mr double dot, I can take it on one side and take all the expressions on the other side. So I will get mr theta dot square minus du by dr. Okay, so that is my expression that I'm getting. Okay, so let's write that down. M r double dot is equal to mr theta dot square minus du by dr. Okay, now is mr square theta dot. Okay, so from here I can say that theta dot is j by mr square. Okay, so that means if I take theta dot square, I will essentially get j square by m square r to the power 4. Okay, now if I plug that into this equation here, okay, to call this equation 3, so I will get mr double dot is equal to mr, and I will get a j square term here, and I have m square r to the power 4 minus the partial derivative of the potential function. Okay, so I have some cancellations here. R will cancel, 1 m will cancel. Okay, so I will get mr double dot will be equal to j square by m r cube minus du by dr. Okay, so that is what I'm getting. So it is a little bit different expression from what I'm used to. Okay, so take a note of what you're getting here. This expression basically says that this is mass times acceleration. So there is some force. Okay, and on the right hand side you have some negative gradient of the potential. Okay, but you have only one term that looks like a potential here. Okay, and look at the equation that we had gotten before right here. Okay, again here you're seeing that you have some force is some mass times acceleration. Okay, so essentially here you are getting an equation of motion. Okay, when you are looking at how this central force is behaving. Okay, so we want to bring this expression into a much more comfortable form. Okay, and the way we can do that is if we introduce a potential that is known as the effective potential. Okay, and we are going to define the effective potential as a quantity that is j square by mr square, and I will have to have a 2 here. Okay, plus mu of r. Okay, and see what we get here. If I take this derivative of this effective potential, okay, that means I'm taking the derivative here. My first term, okay, will become, so I will have a minus 2 because r to the power minus 2 here I'm taking the derivative. Okay, and then I will have a r cube here. All right, and I will have the derivative of u with respect to r. Okay, and this is nothing but minus j square by mr cube plus du by dr. Okay, and I can take the negative sign outside, and then I'm getting j square by mr cube plus du by, so if there is a minus sign then this has to be minus. Okay, so du by dr. Okay, and that is the same expression here. Okay, that means I can write my equation 4 in this form now, that mr dot is equal to minus du of effective by dr. Okay, so you see, again you're getting force is a negative gradient of some potential function. Okay, and later on we'll see what this effective potential actually is. We'll try to plot this function and we'll see what this effective potential really means. Okay, but essentially what you're getting from this solving the radial equation of the Lagrangian is you're getting your equation of motion. Okay, where you're seeing that the force is negative gradient of the potential energy. Okay, and you have some potential energy terms where one of the terms in this effective potential, okay, looks like this j square by 2 mr square. Okay, so this first term looks like it depends on the angular momentum. Okay, so if something is going in a orbit, right, it will have some angular momentum, so then you are getting this term here. Okay, and the second term is just the potential, which is spherically symmetric potential dependent on r. Okay, so these things will be much more clear when we talk about effective potential in the next class. Okay, but for now you can see how the Lagrangian formulation is telling us more about how the system behaves. Okay, so you're getting basically the relationship of the conservative force come out of the picture when we are trying to solve the radial equation. Okay, for the first part, let's derive this Kepler's second law. And we already derived this before as well. But at that point of time, we didn't look at the Lagrangian formulation. Okay. So now, just to remind you, the second law of Kepler says that the vector drawn from the sun to the planet, it will sweep out equal areas in equal time intervals. Okay. So a planet that is going around in an orbit, uh, the area that it covers in certain time, here a1 will be the same as a2 if the time is the same. Okay, so let's try to derive this now using the information that we have gotten from the Lagrangian equation. Okay, so when we solved the angular part of the Lagrangian equation, what did we understand? We got that the angular momentum j is conserved, right? So this is our starting point, that the Lagrangian equation has given us that j is this quantity mu r square theta dot or mu r square omega, and it is a constant. Okay, so if I look at this area that a certain satellite or certain planet is covering, okay, that area I can write it in terms of this expression 1/2 times the radial component r square times the angle that it covers in certain time, okay, which is d theta. Okay, so let's say that the time that we are considering is some time dt. Okay, so Now we want to look at this velocity with which the area is covered. So that is known as the areal velocity. Okay. So we want to find an expression for dA by dt. Okay. So the dA by dt will just be 1/2 r square times d theta by dt. Okay. And d theta by dt is nothing but theta dot, right? So and that is just your expression for omega. But we know the relationship between this theta dot and the angular momentum, okay, which is this value here, okay, which is j by mu r square. So what I can do is I can plug this equation in here, okay. So my dA by dt will be 1/2 times your r square times j by mu r square, okay. So my r square and r square will cancel and I'll be left with 1/2 j by mu, okay. And so you see in my system where I'm considering a reduced mass, okay, my j, which I know is a constant, and my mu, which is a reduced mass, is constant for the system. So my dA by dt, which is the areal velocity, is also constant, okay. So we have just proved the Kepler's second law just by getting the information from the Lagrangian formulation of uh, two masses where one of them is orbiting the other mass, okay. So this derivation that we have just did, right, this is not just specific for your case of gravity, right. So it is a much more generalized expression because it is applicable to all central forces, okay. So it's not just limited to gravitational force, okay. And like we were discussing before, Kepler just derived it empirically, but uh, we can see that the formulation of this second law is much more rooted in the fundamental physics of how this system behaves when there are two objects that are interacting and orbital motion is happening, okay. And till now we have talked about reducing the two body problem to a one body problem. We have looked at your angular momentum, we have looked at kinetic energy, and so obviously the next thing that we want to do is we want to look at the mechanical energy, okay. And we know that the central force is a conservative force, and so it is expected that the total mechanical energy of the system will be conserved, okay. And here you have to be a little bit careful. When we use the Lagrangian formulation, we had the expression T minus U, okay. However, when we are talking about total mechanical energy of the system, the expression is T plus U, okay. So this entire expression is equal to your total mechanical energy, okay. So if you are using the polar coordinates again, so your total uh, kinetic energy T will be 1/2 times your reduced mass mu times this factor which comes from the polar coordinate, right, r dot square plus r square theta dot square, okay. And then you can plug in a spherically symmetric potential here and you can solve for that particular case, okay. So again, in this scenario we can find an expression because we already know what the angular momentum is, okay. So we know j is mu r square theta dot, okay. So that means if I want to replace this expression here, I can do that, okay. So let's try to do that. So I can write an expression for energy as 1/2 mu and have r dot square plus, now I have a r square and I have a theta dot square. So that would mean I have a j square by mu square r to the power 4, okay. So I'm squaring this term right here, okay. And then I have a potential function here, okay. So now I can cancel some of these r's, right. So I will have 1/2 mu r dot square, okay. And I can multiply this mu inside if I want, okay. uh, or maybe I don't want to do that for now. Let's keep it the way it is, plus j square by mu square r square, okay. And that's my first expression, and then I have a u of r, okay. So that is my total energy, okay. And let's simplify it anyways, okay. So I'll have 1/2 mu r dot square plus j square by 2 mu r square plus mu of r. Okay, so that is what I get if I multiply this half of mu inside. Okay, and the reason why I did that is you can now see the similarity. Okay, j square by 2 mu r square plus u of r. What is this term right here? We just defined it, right? J square by 2 some mass times r square plus mu of r is actually the effective potential. Okay, so what we can do is we can write this expression of total energy as 1 half mu r dot square plus mu of effective potential. Okay, so this effective potential consists of this potential term, and this is known as the centrifugal potential. Okay, like I mentioned, this potential is coming because of something that is doing some orbital motion. Okay, and this mu of r, this can be a gravitational potential if we consider the case of gravity. Okay, so when we add both these terms, then you can get the total energy. All you have to do is you have to add the kinetic energy term to this particular system where it is experiencing some potential. Okay. Now, one of the interesting things here is that uh, if I look at this expression and let me see, and I write it in this form now, E minus U of effective, okay, is equal to 1 half mu r dot square. Okay, so I've just taken the effective potential on the other side. Okay, so notice on the right hand side you have mass and you have this r dot, and that is the square term. So this entire term is essentially positive. Okay, so either it can be 0 or it can be positive. So essentially this is greater than or equal to 0 always. So this is a very important construct. Okay, is that your energy, okay, will always be greater than or equal to the effective potential. Okay, so that is what it comes out of this equation. So I just want you guys to be aware of that. Okay, so we just talked about this total energy, right? So we have this expression, okay, which gives you the kinetic energy and the potential energy or the effective potential. Okay, now how is this useful? Okay, now one thing you can do is from here you can look at how an object is orbiting, you know, the sun, for example. Okay, so all you have to do is you have to look at this r that is changing, okay, which is the position vector that is changing with respect to time, okay, and with respect to the angle. Okay, and that essentially is telling us about this two-dimensional orbital motion. Okay, and so to do that you need to figure out how to get these quantities, which is r and theta, and from these equations. Okay, and there is have E, and now I'm going to write it in terms of dr by dt so that it makes more sense as to what we are trying to do. Okay, and we have the expression which is your j square. Let me write it in terms of j square. Okay, j square by 2 mr square plus u of effective. Okay, or sorry, it's u of r. Okay, so that is my expression for the total energy, which is the kinetic energy term plus this effective potential. Okay, now just for consistency, let me just write mu here. Okay, so when I want to find an expression for r, what I'm going to do is I'm going to now isolate this term, which is dr by dt. Okay, so if I do that and keep it on one side, okay, so you can see that I will get this E minus this u of effective term. Okay, and this entire term is mu of effective, right? So let me just point that out. This is mu effective, and what I can do is I have a 1 half u, right? So there will be a factor of 2 by mu here. Okay, there we go. All right, and now dr by dt is just going to be this square root of this value. Okay, so it will be 2 by mu, and I will get E minus u of effective. Okay, and now if I want to find what is the value for r, for example, all I have to do is I have to integrate this. Okay, so what I'm going to do is I'm going to integrate this function, and then I will get r, and then I'll have an integral 2 by mu E minus u of effective. Okay, and this entire thing is in the square root, and then I have dt, and now I'm integrating this, right? So I have taken integral of dr, which is r. Okay, and that's how I know now I have a function of r, what is my position variable. Okay, now similarly, what we can do is we can find the value for the angle. Okay, and before we do that, let me just present the picture here. Okay, the reason why we are doing it is because remember there is an orbital motion happening. So there, these are the two masses, and then they're going and they're doing some motion like this, right? And we are defining in terms of r and theta. That is our polar coordinates, and that is our two-dimensional motion. Okay, so that is what we are doing here. So we are trying to find an expression for how r is changing. Okay, and we are trying to find an expression how theta is changing, and so it is more important for us sometimes to know how theta is changing. Okay, because if you visualize this problem, okay, and let's say I'm looking around from this particular axis. Okay, so when I look from along this y axis, right, I cannot really figure out what the value of r is unless I tell you what the angle of theta is, because when I always look from this particular orientation, my situation will always look like a straight line, right? So always I will see the projection of this planet that is going around this sun. Okay, so it will look to me a picture like this, right? So this value that I'm seeing, which is a projection of this particular value of r on this axis, okay, will not actually tell me the distance between these two planets. Okay, so I have to be very careful that I have to define r and I have to define theta, both of them. Only then I can tell you exactly the distance of how far one planet is from the other. Okay, sorry, one planet is from the sun, okay, that it is orbiting. Okay, so we try to do that. Okay, so we want to find an expression for theta as well. Okay, and just like we did for r, we can do for theta as well. So all we have to do is we have to get an expression of how theta is changing with respect to r. Okay, so I can write it as d theta by dt times dt by dr. Okay, or this you can simply write like this. Okay, so which is d theta by dt divided by dr by dt. Okay, and here again we know that dr by dt is just your r dot. Okay, and d theta by dt is just theta dot. Okay, and moreover we know what j is. J is just mu r square theta dot. Okay, so if we know what theta dot is, okay, which will be j by mu r square. Okay, so I can plug that everything into this equation. Okay, so uh, I already know what dr by dt is. Okay, I already figured that out. It is this expression right here, square root of 2 by mu e minus u effective. Okay, so dr by dt I just proved it is square root of 2 by mu e minus u of effective. Okay, and then my d theta by dr will be d theta by dt is just this function j by mu r square. Okay, and I have another factor here, which is this dr by dt, which is in the denominator. So I have to write square root of 2 by mu e minus u of effective. Okay, and now I have to be careful. There is a mu here. When it goes inside this argument, I have to square it. Okay, so basically I'm getting j by r square. Okay, and I have mu square here and then mu, then one of them will cancel. So I will get essentially square root of, or maybe I should not write square root. I will write it with the parenthesis. Okay, so I will get 2 mu e minus u of effective. Okay, and this entire expression will be raised to minus half. Okay, because I've taken it in the numerator. All right, and now I can integrate this again. So I can find theta now if I integrate this d theta. Okay, and it will be again this integral of this function, which will be j by r square. We just write it clearly. It will be integral of j by r square, and I have a 2 mu e minus So effective is to half, okay, is to minus half times dr. You see, so now I have found an expression for theta in terms of r, and I have found an expression for r as well, okay, from my equations that I had previously gotten from my total energy that I got from my Lagrangian formulation, okay. And there is a lot of hidden information that is present here, okay. So we'll be trying to explore that as well, okay. So, and one of them is where we'll conclude today is the so-called turning points, okay. So if I look at this orbital motion, okay, and I look at this specific condition as to what happens when my E is actually equal to mu effective. If these two quantities are equal, then I'm getting that dr by dt is equal to 0, right? E minus u effective is 0 because they are same. So my entire expression dr by dt is actually 0, okay. So that means the change is 0, okay. So that I have a minima here, okay. So where is this situation happening? So if you look at this simulation here, Earth going around the sun, right? So obviously, as you can imagine, as the Earth is coming close to the sun, it is getting it's speeding up, okay, and it slows down as it goes farther away, okay. But notice some peculiar things that are happening here, okay. And one of the things that is happening is that if I just try to look at the position coordinate, okay. So I have my one position here, okay. Let me use another pen. So one of the coordinate is here, okay. So I am trying to see this distance r, okay, of this planet here. So now, if you notice what is happening to this, okay, r is actually changing, right? And how is it changing? It's actually increasing, okay. So if you look at this farthest away point right here, okay, this is when you have the maximum value of r, okay, and diametrically opposite here at this position you're getting that this value is where r is going to be minimum, okay. So there is region here, okay, from let's say 1 2 and let's call this 3 and let's call this 4, okay, and let's call this 5. So in the region 1 2 3, what is happening? The r is actually increasing, okay, and in the region from 3 to 5 your or 3 to 5 to 1, okay, r is actually decreasing. You can see that, right? The position coordinate r, right, as this earth is approaching closer to the sun, right, it's slowing down, right, and here and then it speeds up and this r coordinate is actually decreasing and then the r coordinate starts increasing, okay. And this point 3 and 1 is where this change is happening, whether the r is increasing or r is decreasing, okay. So technically speaking, this 1 and 3, these are called the turning points, okay. And here you're getting that this E is actually equal to your effective potential, okay. And that is what you're seeing from these equations right here, okay, that when E is equal to U effective, dr by dt is actually 0. So there is no change happening at this farthest most point, okay. And that is what visually you can see from this motion of the earth going around the sun.